Welcome friends, Igor is here, and in this video we will consider subspaces of vector spaces. In this lesson we will define the notion of a subspace of a vector space, discover an efficient test to determine if a subset of a vector space is a subspace of that space, and prove that the null space of a matrix is a subspace of a vector space of column vectors. Let's get started. Here's an idea for a notion of a subspace. A subspace is a vector space in its own right that lives within another bigger vector space. Suppose we have two vector spaces V and W with identical operations of vector addition and scalar multiplication. Moreover, let's assume that W is a subset of V. Then we say that W is a subspace of the vector space V. Let's look at a simple example. Our ambient vector space V is C3, the vector space of column vectors of size 3. In this vector space, we are going to consider a subset W, which is defined as follows. The third component of the vector must be equal to 0. We have explicit operations of vector addition and scalar multiplication in the vector space C3, and elements of the set W are also elements of the ambient vector space C3. Therefore, we can apply these given operations of vector addition and scalar multiplication to the elements of the subset W. W is going to be a subspace of C3 as long as it itself forms the structure of a vector space with respect to these operations. To verify that a structure is a vector space, we need to make sure that it satisfies 10 vector space properties. And this is no easy task, because it takes quite a bit of time and effort to verify all 10 properties. However, in this situation, we have an extra assumption, namely, this set W does not exist in a vacuum. It is a subset of what's already known to be a vector space. This tells us some information about the operations that we are going to transfer to the subset W. So maybe some properties of the vector space will automatically transfer from the ambient space C3 to the subset W. Let's go back to the general setup. We have a vector space V and we have a subset W. Let's see which properties of the operations in V automatically transfer to the properties of the subset W. We will take one vector space property at a time, and we will decide whether this property automatically holds for subset W or if it needs to be checked separately. Does this property automatically hold for a subset of W? Let's think. If we take two vectors in a subset W, then we know that they are vectors in V, and therefore their sum is a vector in V. Are we guaranteed that the sum of these two vectors has to be back in our subset W? Not at all. Therefore, this property does not automatically hold for W. Next is the property of scalar multiplication closure. Let's take a vector U in the subset W. Let's scale this vector by scalar alpha. What we know is that this scalar multiple is an element of a vector space V, because the vector U is an element of V. Are we guaranteed that this scalar multiple remains back in that subset W? Unfortunately, no, and therefore this property does not automatically transfer to subset W. Looks like we didn't have a great start. So far 0 out of 2. But let's keep working. For the next property, if we take two vectors in a subset W, then we know that they are vectors in V, and this property does hold for all vectors in V. In particular, it holds for all vectors in W. Therefore, this property does transfer to a subset. Looks like we finally caught a break. Next, the associative property. We know that it holds for all vectors in V, therefore, in particular, it holds for all vectors in a subset W, so this property is also automatically satisfied. Next, the zero vector property. We know that there is a zero vector in the vector space V, Do we know that it falls within the subset W? No, we can't guarantee it, and therefore this property does not transfer. When it looked like things finally started going our way, this happens. Next, the additive inverse property. We know that each vector in V has an additive inverse in V. Therefore, the vector u in W does have an additive inverse somewhere in the space V. Do we know if this additive inverse falls within the subset W? No, we don't, and therefore this property also does not hold. Next, we know that this property holds for all vectors in the vector space V, therefore it also holds for all vectors in the subset W, so this property does transfer. This property holds for all vectors in the space V, therefore it also holds for all vectors in W. Same idea for the next property. It holds for all vectors in V, therefore it holds for all vectors in W. Finally, this property also holds for all vectors in V, therefore it holds for all vectors in W. So, in the end, we did not do so bad. 6 out of 10 properties will be inherited automatically by any subset of a vector space, and it only remains to check that the subset satisfies the 4 properties that are not guaranteed to transfer. Here is a bonus for those who made it thus far. I am going to show that in fact you need to check only 2 of these properties, property number 1 and property number 2. Let's establish the following simple and efficient test for subspaces. Suppose we have a vector space V and a subset W of this space. Then the subset W is a subspace of the vector space V if and only if the following 3 conditions hold. First of all, the subset must be non-empty. Second condition, the subset must be closed under vector addition. This is property number 1 of vector spaces. And condition number 3 is that this subset must be closed under scalar multiplication. This is property number 2 of the vector spaces. This is an if and only if statement, and therefore there are 2 implications for us to establish. Let's start with the forward implication. We are going to assume that the subset W of V is a subspace of V, and then we need to prove that the 3 conditions are satisfied. When we assume that W is a subspace of the vector space V, we are assuming, by the definition of the subspace, that W is a vector space in its own right. In particular, it cannot be empty because it must contain at least the 0 vector. Moreover, the other 2 conditions must be satisfied because this is a requirement for a vector space. It is the opposite implication that is essentially of interest in this theorem. We are going to assume that we have a subset W of a vector space V which satisfies the given 3 assumptions. It is a non-empty set, it is closed under vector addition, and it is closed under scalar multiplication. We need to prove that then W is a subspace of the vector space V, which means we need to prove that W is a vector space in its own right with respect to the 2 operations inherited from the vector space V. To check that W is a vector space, we need to verify that all 10 properties of the vector spaces hold for W. But we just had this earlier discussion which showed that in fact, because W lives inside a vector space, 6 of the 10 properties are automatically satisfied, and all we need to make sure is that 4 properties hold for W. First, we need to make sure that W is closed under vector addition, but this is assumption number 2 here. Then we need to make sure that W is closed under scalar multiplication. This is assumption number 3 here. Then we need to check that W contains the 0 vector. And finally, we need to show that every vector in W contains an additive inverse in W. So, what we need to check is that W has the 0 vector and every vector has an additive inverse in W. Let's do this. Let's take any vector in the subset W. This is possible because we assumed this subset is not the empty set. This vector is a vector in the ambient vector space V, and we already proved in the previous video that in any vector space, if you scale a vector by zero scalar, what you get is the zero vector. But we assumed that a scalar multiple of a vector from W remains inside W. This proves that the zero vector is part of W. To complete the proof, it remains to show that every vector in W has an additive inverse in W. So let's take any vector x from W. Again, in the previous video, we proved that in any vector space, in this case, this is the vector space V, the additive inverse of a vector can be obtained by taking the scalar multiple of the vector by the scalar -1. But we also assumed that if you take a vector in W, then a scalar multiple of this vector remains in W. This shows that the additive inverse of the vector x is still a vector in W, and therefore this completes the proof that W satisfies all 10 properties of the vector spaces. That means W is a vector space in its own right, and therefore it is a subspace of the vector space V. Let's apply this test for a subspace. Our ambient vector space is P4. This is the vector space of polynomials of degree at most 4. And we will take a subset W, which is defined as follows. It consists of all polynomials from P4 such that the value of the polynomial at 2 is equal to 0. To see if this subset is a subspace of P4, we simply need to go through the 3 conditions in the test. First, is this subset non-empty? Can you come up with at least one polynomial of degree at most 4 that has 0 value at 2? Sure, for example, the polynomial x minus 2 is an example of such polynomial, and therefore this is a non-empty set. Second, we need to check that the subset W is closed under vector addition. Let's take 2 arbitrary elements of W, polynomials p and q, and we need to check if p plus q belongs to W. The criterion for membership in W is simple. We just need to make sure that the value of the polynomial at 2 is equal to 0. And this simple verification ensures that indeed p plus q is a member of W. Last condition, we need to check that W is closed under scalar multiplication. For this, we take an arbitrary element p of W and any scalar alpha. We need to check if the scalar multiple of p by alpha belongs to W. To conduct this check, we simply need to compute the value of this new polynomial at 2. We see that it is equal to 0, and therefore the scalar multiple is still an element of W. We completed our 3-step check, and this shows that this subset W is in fact a subspace of the vector space P4. For contrast, here is an example of a subset of a vector space which is not a subspace. For the ambient vector space, I'm going to take C2, vector space of column vectors of size 2, and a subset consists of those vectors which have the property that their components multiply to 0. It is easy to see that this set is not closed under vector addition. Here is a counterexample. Because one of the conditions in the test for subspace fails, we conclude that this subset X is not a subspace of C2. It's natural to ask what are the possible subspaces of any given vector space, and we can answer this question partially right now by producing 2 trivial examples of subspaces. The first trivial example is the vector space itself. The second trivial example is a subset which contains only the 0 vector. It is easy to see that this is a subspace by going through the 3-step test for a subspace. Is it non-empty? Yes, it contains the 0 vector. Is it closed under vector addition? Yes, because 0 vector plus 0 vector is the 0 vector. It's back in the set. Is it closed under scalar multiplication? Yes, Because we proved that in any vector space a scalar multiple of the zero vector is still the zero vector. The reason we call these two subspaces trivial is because they exist in every vector space. Every vector space has a subspace itself and a subspace which contains only the zero vector. Let's record this observation for future reference as a definition. Why do we need this definition? It's because now we can talk about non-trivial subspaces. A non-trivial subspace of a vector space is a subspace that is not just the zero vector and not all of the vector space itself. And now we can justify the terminology for the null space of a matrix. We didn't call it just the null set, it was a null space. And now we can prove that in fact the null space of a matrix is indeed a vector space. It is a subspace of the space of column vectors of an appropriate size. For this proof, let's recall what the null space of a matrix is. It is the set of all solutions to the homogeneous linear system with the matrix as the coefficient matrix. And with the tool of matrix multiplication, we can write linear systems using matrix vector products and vector equalities. Therefore, the null space of a matrix A consists of all column vectors x such that matrix x multiplied by the vector x is equal to the zero vector. Is the null space of any matrix non-empty? Yes, because there is always the trivial solution. This is a property of all homogeneous linear systems. Is it closed under vector addition? Let's take two elements of the null space, vector x and vector y, and we would like to check if x plus y is an element of the null space. For this, we are going to consider the matrix vector product. We know that matrix multiplication distributes over addition. Also, x is an element of the null space of A, therefore x is the zero vector, and y is an element of the null space of A, so ay is the zero vector. Zero vector plus zero vector is the zero vector. This computation shows that the vector x plus y belongs to the null space of A. Finally, is it closed under scalar multiplication? Let's take any vector x from the null space of A and any scalar alpha. We'd like to check if the scalar multiple alpha x is in a null space. For this, we consider the following matrix vector product. We know that in a matrix product, we are free to move the scalar anywhere, so I'm going to move the scalar alpha in front of the expression. X is an element of the null space of A, therefore the matrix vector product AX is the zero vector, and a scalar multiple of the zero vector is the zero vector. This computation shows that the scalar multiple of X is still an element of the null space. This completes our proof that the null space is a subspace of the vector space of column vectors. If you found this video useful, and how could you not, when I reduced the need to check 10 properties down to just 3, then please give this video a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will prove that the span construction results in a subspace, and in particular, the column space and the row space of a matrix are in fact vector spaces. I will see you later.